K1 is non-zero, or K2 is non-zero, you can divide K1 or K2 on both sides. So either you have Y1 it's a multiple of Y2, or Y2 is a multiple of Y1. So you always can have either this or this one. Right? Now, so we see that so Y1, right? Y2 prime minus Y2x, Y1 prime x. Okay. Now we compute this expression. Okay. And we know, for example, we have two cases. For first case, that y1 can be expressed as k times y2. So it's k y2x y2 prime minus y2x, and y1 prime is equal to k y2. Okay. This is for the first case. For the second case, we have LO y1x y1x times LO y1x and y1x. Okay. Now you can see, no matter which expression, you cancel them, right? So the result is 0. So this function, because this expression actually is a function of x, but they cancel each other. So you can see that is 0. Okay, so this is a necessary condition. It's necessary. So suppose y1 and y2 are linearly. Dependent. Okay. I'm sorry. Y1 and y2 are linearly dependent, so there exists their cases. So this should be dependent, not independent. So if y1 and y2 are linearly dependent, then this expression is 0 functions on the whole open interval I0. Surprisingly, okay, this necessary condition is also sufficient. But in much weaker form. So we will see that this condition is also sufficient, but in a much weaker form. We will see what do I mean a much weaker form. Okay, before that, we define the Wronskian. Sometimes people call it our Wronski determinant. Okay. Alright, so define the Wronskian of two differentiable functions. F of x and g of x on an open interval I0 as W F G. Okay? So the Wronskian of two differentiable functions f and g is the determinant of this matrix. Okay? So this is f of x, this is the first derivative of f of x, this is g of x, and here is the first derivative of g of x. And we take the determinant. So you know how to compute the 2x2 determinants, right? And this is equal to f of x times 3 prime of x minus f prime of x times 0. Okay. So it's called the Wronski determinants or Wronskian. Wronski is the name of a mathematician. Okay, now, and which this Wronskian, which is a function I0. Okay, so Wronskian actually is a function on I0. All right, now we can state theorem 2.2 is about linear independence. Of solutions. Linear for DE based on order. Okay. So now let's the coefficients P of x and the Q of x of the homogeneous linear ODE of second order in 2.3 continuous. Open for okay, so suppose we know the two coefficients Qx and Qx of the homogeneous linear ODE. We write P. So actually we wrote this ODE in the formula 1.6.3, and we assume these two functions are continuous. Okay. Then two solutions. Okay, y1 and y2 of 2.6.3 are linearly dependent. Okay, are linearly dependent. And the only layer Wronskian the Wronskian is 0 at some point x0 and y0. Okay? It's very weak. You know, this is a different only condition. You just need to compute the Wronskian and inspect that in this open interval, there exists a point x0 such that the Wronskian has value 0. At this point, only one point is enough. Only one point. The necessary condition tells you the Wronskian is identical to 0 functions on the whole interval. It means that the Wronskian is 0 at every point on the interval. This is the necessary condition for linearly independent condition. Alright? So this is the necessary condition. But for sufficient condition, we don't need to check that the Wronskian is identical to the 0 function. Only. You just need to check only one point. Okay, if you see in this open interval that there is a point x0 such that the Wronskian is 0. Remember, Wronskian is a function of x. It's a function. So you just need to check only one point. Furthermore, if the Wronskian is 0 at x0, I0, then the Wronskian is identical to 0 on I0. So if there's one point such that the Wronskian has 0 value, then the Wronskian itself is the all 0 functions on very strong. Okay? It is very strong. Hence, if there is an x1 I0 at which the Wronskian is not 0, then y1 and y2 are linearly independent. Okay, so it turns out that to check two functions, two solutions are linearly independent. You only need to check that the Wronskian has non-zero value at a certain point. Only one point is enough. Only one point is enough. So before I give a proof, please let me know if you have any question about the statement of this theory. With this theorem, it will be very convenient to check whether two solutions are linearly independent or not. Because when you are given two solutions, y1 and y2, you form the Wronskian. Okay? It's very easy, right? Compute this Wronskian. This Wronskian basically is a function of it. And you can refine a point. So you just put a point x0 into it. To see the value is 0 or not 0. If it's 0, then y1 and y2 are linearly dependent. If it's not 0, then y1 and y2 is linearly independent. very simple and very easy. Just pick up a point and evaluate the value of the Wronskian at that point. Okay? Fine? Good. So now I'll give a proof. Okay? I hope I can complete the proof at the end of the class. So the proof, in this book I do not assume you have taken linear algebra already. Okay, I'll assume you are still taking linear algebra. Okay? So it is because I was doing some matrix operations, even though it's 2 by 2. All right, the direction we have done. Because if y1 and y2 are linearly dependent, okay, so if y1 and y2 are linearly dependent, we know the Wronskian is identical to 0 function already. Right? So of course, this is true. Right? So we have done. So now we have to do the reverse part. Okay? It's not trivial. Not trivial. Okay, so we suppose that the Wronskian y1, y2 is 0 at a point x0 equals 0. Okay, so now we suppose that the Wronskian is 0 at some point x0. And we have to prove that y1 and y2 are linearly dependent. Okay? We have to prove that. Right, so i.e. the Wronskian y1 x 0, y2 x 0, y1 x 0, y2 x 0, y1 prime x 0, y2 prime x 0, and y1 x 0, y2 prime x 0, minus y1 prime x 0, y2 x 0, which is equal to 0. Okay, so we are given this value. Okay, we are given this value. Now, to show these two solutions are linearly dependent, we have to find the two constants, k1 and k2, not both 0, such that k1 times y1 plus k2 times y2 is identical to 0 function. Right? How can we find k1 and k2? Well, so we consider the following system of linear equations with unknown k1 and k2. Okay, so the question is k1 times y1 x 0 plus k2 y2 x 0 k1 y1 from x 0 plus k2 x from x 0. Okay, so we consider the following system of linear equations. Remember, y1 x 0 is known, y2 x 0 is known. y1 from x 0 and y2 x 0 are all known, right? Because we are given two solutions, okay? And we know that this Wronskian is 0 at 7 for x 0. Now in matrix, So this system of linear equations, I believe you already studied this system of linear equations in your linear algebra course. Okay, so we can express such a system by a matrix equation. Okay, so now we have a homogeneous, all right, system of linear equations. Right? This is a homogeneous system of linear equations. Okay. Since this matrix, the matrix has determinant, which is equal to 0, right? By our assumption. So the matrix is what? It's not invertible. Do you know the fact? A 2 by 2 matrix is invertible even only if its determinant is non-zero. Did you learn this from high school? If you know, please raise your hand. Okay, so you all know, or you don't know?
I know.
Oh, you know. Okay, good. All right, so the next question is that in linear algebra, you should learn that if the matrix is not invertible, means the matrix is singular. You know the terminology singularity? You know that? So if this matrix is singular, then the system of homogeneous linear equation is non-zero solution. You know the fact? You can always find solution k1, k2, which is not equal to 0 vector. Right? If you don't know the fact, please raise your hand. Are you? You don't. You know. No, you don't know. Okay. Okay. Since one of you don't know that, I have to solve it right now. Okay. So I solved it by elementary method. Okay. So now, if both y1 x0 and y1 from x0. So if the first row is 0, means that both are zeros. Okay. Then k1 equal to 1 and k2 equal to 0 are alright, is the solution of this system. Is that correct? If this is 0, this is 0. Now I let k1 equal to 1, right? And k2 equal to 0, then these two equations are satisfied. So I found a solution, right? k1, k2. And these two are not both 0. Okay, so I found solution. Now, if y1 x 0 is not equal to 0, so suppose this number is not equal to 0, then by elimination, right? So the elimination is here. So this is something like we multiply minus y1 from x 0 divided by y1 x 0. All right, so we multiply this to here. Okay, so we have maybe I have to multiply here. if I multiply okay, so I multiply the first row by this constant and add to the second row. I will cancel this entry, right? This is so-called elimination, or people say Gaussian elimination. And so this is 0. Yes. And here we have y2 prime that's 0 minus y1 is 0 and the y1 prime is 0 times y2 is 0. Okay. And the k1. Okay. So when we do so we multiply, so actually basically the first row, the first equation multiply with this constant and add to the second equation. So the second equation becomes to a simple one, this one and this. And look at this entry. This entry actually is equal to y1 x is 0, and this is y1 x is 0, y2 prime x is 0, minus y1 prime x is 0, and which is equal to 0. So this entry is 0 too. So basically we cancel the second equation. Okay? So we end up with y1 x is 0 and y2 x is 0. So by elimination, the system of linear equations becomes to an equivalent system linear equation. So basically, we have only one. And so, and we have a solution. The solution is that k1 can be put into y2 x is 0, and then k2 is equal to y x. Okay? Right, so this is the solution. And because y1 x0 is not 0, this is not equal to 0. So we know k1 and k2 are not both 0. Again, right? The point is that we want to find k1 and k2, which are not both 0. So for the first case, we find a solution k1 and k2, which are not both 0. For the second case, we find a solution k1 and k2, which are not both 0. Finally, if y1 prime x is 0, not equal to 0. Now suppose this is not equal to 0. It's possible this is equal to 0, but suppose this is not equal to 0. Then, by doing the same elimination steps, then we have a solution. K1 is equal to minus y2 prime x is 0, and the k2 is equal to y1 prime x is 0, and which is not equal to 0. Okay, now, so in any case, all right, we consider three cases. The system, okay, the system of homogeneous linear equations, okay, is a solution for which K1 and K2 are not both 0. This is the point. K1 and K2 are not both 0. Okay? Okay? So now, consider the following function. Y of x equal to K1, y1x plus K2. Alright, so we find K1 and K2 from solving this system of homogeneous linear equations. And we know K1 and K2 are not both equal to 0. Alright, so we find that. Now, which is apparently, right, a solution of the homogeneous linear ODE. Okay? You know already that, because y1 is the solution, y2 is the solution. So by superposition principle, again, right? Remember that? We have the superposition principle for solutions of homogeneous linear ODEs. So apparently, this function is a solution of 2.612. Okay, by the superposition principle. Okay. Now, we have two initial conditions. The two initial conditions are yx0. What is yx0? Yx0 is k1, y1x0 plus k2, y2x0, which is 0, because we deliberately ask for that, right? Here. So y0 is 0, and the y prime x0, k1, y1 prime x0 plus k2, y prime x0, 0, 2. Okay, so this function satisfies the homogeneous linear ODE of second order with two initial conditions, which are always true. But the trivial solution, y star x equal to 0 and I 0 is also a solution of 2.612, okay, with the same initial conditions. Because it's always your function, so of course, at any point x0, the value is 0, and the derivative at x0 is 0. Okay, so this is solution. Y star and y, they are solutions of the homogeneous linear ODE of second order, and they have the same initial conditions. Now, theorem. So by the existence and the uniqueness theorem, i.e. theorem 2.6.1, right? I stated the theorem at the beginning of this section. Okay. We know that y x must be equal to y star x. So we prove that this function y x actually is equal to 0 function. Okay, so this implies that y1x and y2x are linearly dependent. Okay, so we prove yx is equal to the 0 function by using the existence and uniqueness theorem. Any questions? Up to here? Yes, please. Oh, we just pick up a solution. You can pick k1 equal to 2. Yeah, because this is 0 and this is 0, right? So we can put any k1. So I just select k1 to be 1 and the k2 to be 0. There are many solutions. Yeah, so I just pick one. One is enough. Yes, please. Yeah, if it's singular, there's no inverse matrix. Yes. If there is no inverse matrix, it means that we have a non-trivial solution. Because if this is invertible, there is only one solution, which is 0. Right? If you have a matrix equation, if A is invertible, you can multiply A inverse because any matrix multiplied with 0, column is 0, right? But this is equal to x, right? And x equal to this is only solution. It's called not trivial, only trivial solution. But if A is singular, then you have a non-trivial solution. This is the beginning of linear algebra. You have to learn, and you should learn that. Okay. If you don't know this factor after you learn, the linear algebra, then you should fail this course. I think your professor should fail you. Yeah, this is very fundamental. You have to know that. Okay. So I just use this very basic fact from linear algebra, but since one of you don't know this fact, so I have to solve it. Okay, one by one. Okay. So anyway, so up to this point, we have used a very big tool. This tool is theorem 2.6.1, the uniqueness, the existence and uniqueness theorem. Okay. Without this theorem, we cannot reach to this conclusion. Okay. To say that this function is identical to 0. Okay. So theorem 2.6.1 is very important. Very important. Any questions? Okay, good. Now, so we have this conclusion, but we have something to prove, right? So, and by the necessary condition. The necessary condition says that if these two solutions are linearly dependent, then the Wronskian y1 and y2 should be identical to 0 or I0. Right? We put a proof. the Wronskian is identical to 0. Here, the Wronskian. Okay. Hence, if the Wronskian of y1 and y2 not equal to 0 at some point x1 in I0, then y1 and y2 are linearly independent. Because if this is true, then the Wronskian cannot identical to 0. And then so y1 and y2 is not linearly dependent. Right? So this is the end of the proof. Okay, so now we can answer a couple of questions. Wow, I have only 10 minutes left. Okay, so the first question is about how do we know that a general solution how do we know that the homogeneous linear ODE of second order in 2.613 has a general solution? Right? How do we know? In the previous sections, we usually said, okay, this is the general solution. So we try our best to find a general solution. But how do we know that? How do we know this is always true for any homogeneous linear ODE of second order? How do we know that? Existence of a general solution of homogeneous linear ODE of second order. Okay. Alright, so is that if P of x and the Q of x are continuous. An open interval I0. Then the homogeneous linear ODE of second order in 2.3 as a general solution on I0. Okay. So this theorem says yes, you always has a general solution. Okay, so we fix, first of all, we fix an x0 in the open interval. So we fix and x0. Now, by theorem 2.6.1, okay, the fixed theorem. Okay. The ODE in 2.6.3, 2.6 means the homogeneous linear ODE. Okay. As a solution. Okay. Set y1 from I0, satisfying the initial conditions. y1 x0 equal to 1 and y1 from x0 equal to 0. Okay, so for this homogeneous linear ODE of second order, together with two initial conditions at x0, we have one and only one solution. Right? This is from theorem 2.6.1. And we call this solution as y1x. Alright? So has this. And a solution y2x on I0 satisfying the initial condition. Y2 x0 equals 0 and y2 from x0 equals 1. Okay, so y1 has initial conditions that y1 x0 equal to 1 and y1 from x0 equal to 0. But for y2, the initial conditions are y2 x0 equal to 0 instead of 1, and y2 from x0 equal to 1 instead of 0 for y1. Okay, so we deliberate set two different set of initial conditions to find two different solutions. Now, we apply theorem 2.6.2 to say that y1 and y2 are linearly independent. Why? Well, the Wronskian of y1 and y2, okay, as at x equal to x0 as the value, okay, y1 x0, y2 x0, okay, which is y1 x0, y2 from x0, minus y1 from x0, y2 x0. Okay, the Wronskian of y1 and y2 at x0 has a value which is equal to, by our setting, is 1 times 1 minus 0 times 0. So it's equal to 1, which is not equal to 0. Now, the Wronskian of y1 and y2 has a non-zero value at certain point. Alright? So, by